All right, let's try this anyway. All right, class.
Yes.
Thank you very much for showing up today. I'm not implying that there's a bunch of slackers that decided not to. And I know everyone makes sure that their earbuds are off and away. No matter how cold their ears are, you don't have to wear ear mufflers in here.
You can write in English?
Who's English?
You can write in English? You can speak English? We can? Yeah. Oh, I didn't. You didn't do my bad.
Wow. That's messed up. Anyway, all right, for people that are actually following along, who read? What page are we on? 41 today. So 41 today. And so that means 40 is going to be where you write down the problems, right? Okay. Trees and the previous one that we did with the weighted circuits, the Eulers, the Hamiltons, all those right there. Writing them out and drawing is going to be key to be effective at solving every single one of these. So, okay, now for the trees, is a graph that is connected and has no circuits. No circuits. So what does that mean? No, you can't go all the way back around. Okay, so but it's actually branching off in different directions. And they're going different ways. So no circuit means that in between your two branches, you're going to have somewhere in between where you will be able to go make a lap. Make a lap in there. Keep going around. So every single one of these branches have to go off onto its own, not going directing you to a new one. So if we think about it, a tree, you don't see trees that actually have a branch going out this way, then all of a sudden that branch is all melded in and connecting to another one, right? No, you don't see that. Okay. What?
African trees. The savannah tree.
Yeah, but they're still not like melding together and like making a they're not doing that. Okay, anyway. All right, so all trees have the following properties. There is one and only one path joining any two vertices. That means that there is one path from Hobby's house over to Lucky's house. That's it. Only one path. No matter how you go. Just one path from go to there. Every edge is a bridge. Every edge is a bridge, so connecting in between those, I can only take them one time. A tree with n number of vertices must have n minus 1 edges. N referring to how many letters, how many dots, or how many houses that we're connecting. And then we would must have n minus 1. So if there is 6 houses we're connecting, that would be 6 minus 1. That would be 5 bridges connecting all of those. That's what we would have. Which of the following graph is a tree? Why or why not? Now, let's look at this first one here. We have 1, 2, 3, 4, 5. I have 5 vertices there. How many bridges or edges should I have? I just did the math a moment ago, and Javi. What did I say in the previous one? I must have n minus 1 edges, right? So if n is the number of vertices, how many vertices did I count up? I have 5 vertices. 1, 2, 3, 4, 5 vertices. So, how many edges should I have there? Nope. 4. N minus 1. So there should be 4 edges. But how many edges do I have? I only have 1 edge. So therefore, this one is not going to be a tree because it does not have enough edges. Does that make sense? Okay. So this one is not enough edges for this first one. This one, might as well just write it in here. B. Let's look at this second one. No. Dos, tres, cuatro, cinco. Cinco de vertices. The vertexes. Right? So, how many edges should I have there? Try again. Not 5. 1, 2, 3, 4. Hey, there it is. There's 4. If n is 5, that means I have 5 vertices, n minus 1, so 5 minus 1 is 4. I have the right amount of edges. Is every single thing connected? Is there only one path to go from A to E? Yes, there is. So this one is a tree. This one is a tree. Now let's next one. Let's count. 1, 2, 3, 4, 5, right? Now let's count the edges. 1, 2, 3, 4, 5. Uh-oh. There's too many, right? Okay, there's too many, but there's also another thing that I want to point out. Right here, this part is a circuit. Yeah. There is a circuit here. So I could just keep going around CDE. So there is a circuit there. So this one is a no for 2 reasons. One, it has a circuit, and it has too many edges. circuit. There we go. So it has a circuit and too many edges. Yes, that guy. Yeah, go ahead. Subgraph, spanning trees. A subgraph is a set of vertices and edges chosen from among those in the original graph. Okay? So the original graph is here. We have A, B, C, D, E, F, G. Okay? So that itself is the original graph. Now the subgraph, we're not going to be using all of them. We're not going to be using all of them, so we're going to start taking out parts of it. So a subgraph that contains all of the connected graph's vertices, that means all the points are still there, contains no circuits, is called a spanning tree. The 2 subgraphs of the previous example are spanning trees. Now if you look right here, so what did I do? So we went A, E, right? That one's still there. To B, that one's still there. That one's still there. That one's still there. And is that one still there?
Yes.
Yes. What did we do? What did we take away?
We got rid of B and C.
We took away BC. By taking away BC, I was able to turn that from a non-tree because of a circuit and turn it into a tree because it no longer has that circuit. Now this next one, we're going to do the same thing, but if you notice, what did we remove this time? EG, just by removing, so 1, 2, 3, 4, 5, 6. There's 6 edges there, and 1, 2, 3, 4, 5, 6, 7. Okay, so n equals 7. And so my edges, I have 6 edges, so that works there. So by removing certain pieces, I could turn it from a non-tree, right? A non-tree into a tree by a subgraph. By just removing a certain part of it, I'm not taking away from the original. I am just rewriting it so that it will work. Does that make sense?
Yeah.
Is that nonsense? Is that crazy?
You're crazy.
I know I am. I woke up this morning and decided to come to school and teach, lovely high school students math. So I must be. I know, right?
You call me lovely, bro.
I know, right? I know. Why are you so hostile here?
What do you mean, thank you?
What? What do you mean, stay off my phone and quit playing Tecmo Bowl?
I'm not playing
Retro Bowl,
I'm not
fool!
playing Retro Bowl.
Doctor, do me a favor. Confiscate this guy's phone.
I'm not doing anything.
Uh-huh, yeah, that's what I thought. Find a spanning tree for the graph. I would like all you people right now, you are going to try this one. You are going to try this one. I'm waiting because I know what's going to happen. As soon as I walk away, you're going to be like, oh yeah, we started down already.
Turned it up? That's crazy.
Because you wouldn't be playing on your cell phone during class, would you?
No.
You wouldn't do something like that, would you?
No.
You staring at him. You got to do it too. You're down here.
Yeah, bro, we're down. At least I know where we're at.
Uh-huh.
Do we have to, what's it called, take away?
Yes. Take away.
Oh.
Now, what are we taking away?
Take away,
Okay, but before you do that, something else is it. Do something first. And it was the last thing I did on the previous slide. But you need to write it down because someone was playing on the phone. Where did I get that number from? Ooh, wow, someone might have learned something. You got it.
hey, you should get like a.
Oh, I do. I have that one, but that one's actually serious child abuse. This one leaves a good sting mark, but that one, but that one right there will actually do some damage.
That's what I was gonna say, like, if you wanna have.
You know what's actually funny? A parent actually bought me this one because their kid was being a moron and broke my other rulers. So yeah, they brought me a good ruler. So, and with the instructions to beat their kid and didn't mess up again. Get a word.
Mister, can we take more than one?
There's more than one, yeah.
No, can we take more than one?
Yes. Okay, for those people that follow along and pay attention, what is my N? 7? 7.
All right.
1, 2, 3, 4, 5, 6, 7, 8.
Do you take one?
There's 8, right?
Yeah.
So N equals 8. So that means I should have how many edges?
No,
7 edges.
at least I
There we go. 7 edges. And didn't pull out the phone and stare at the Retro Bowl yet.
I'm
Dude.
checking the time.
Dude,
I'm
why is
checking
it?
the
The thing
time.
is attached to your hand every time I look up.
I'm checking the
How
time.
dare you? The audacity of this. Anyway, all right. So we can only have 7, so we have to connect them all. So let's just start by connecting the ones that we have. Let's go 1, 2, 3, 4, 5, 6, 7. Yours doesn't have to be exactly the same, but if you notice, by doing that, I actually have a white marker here. So by doing that, I could actually get rid of that, that. Now, are all of them connected? There's only one road to go from B all the way to G, right?
Yeah.
Okay, there's only one road. And is there anywhere on that where I could make a circuit? No circuits on there, right?
No, sir.
So, that's the best way to actually go through. Start this off, count them up, okay, whatever your n is, do n minus 1, write down how many edges you're going to have, and then connect each one, okay? Connect each one and go over it to make sure that both sides are at least connected to each other. So like the AD, you would still have to have something in there, okay? Is that pretty easy now? There you go. Now, before we actually get into the minimum spanning trees, I'm going to save that one for tomorrow. I'm going to get you guys starting on your homework right meow. So, when we do this one right here, we're going to have to do like mapping it out and going to actually have a little bit more of this. I want you guys practicing on your homework first. So, make sure you all like, share, and subscribe. Hit that notification button. Support my channel. Buy stuff from the merch store.